All right, just a quick introduction to what's called the photoelectric effect. Oddly enough, this was the only Nobel Prize that Einstein won was for the explanation of this effect. Einstein didn't do experiments, but it was his explanation of experiments at the time in which the effect was observed that earned him the Nobel Prize. So what happens in the experiment is people observed that if you shot light at a metal surface, that electrons could be emitted from the surface, all right? And at that time, people were very convinced that light was a wave. So why that was? Why did people think that light was a wave? Well, first of all, they had seen effects like interference patterns, like the double slit experiment. Interference, like the double slit, for example. And then the other example of interference would be, for instance, thin film interference. So those colorful fringes you see when light, some light hits the front of a film and some light hits the back surface, and those light rays interfere. So thin film interference. Right. So people were pretty convinced that light was a wave. And so what they thought was, well, okay, if we do this experiment and light's a wave, one hypothesis was that if you turn the frequency up, you would get more electrons. And the other one was that if you made the light brighter or higher intensity, that you'd get faster electrons. Now, why did they think that, right? Well, you have to realize they're in a wave picture for light. And so the idea here is, well, higher frequency, that basically means like more peaks. Right, more peaks per second. And so those peaks would come down and hit the surface. So as silly as it sounds, I'm going to say like more like slaps to the surface. Like each peak comes down and bam, you hit the surface. So more slaps to the surface. And then the idea was, well, okay, well, you're slapping the surface more often, so you're just going to slap off more electrons. Okay, so more electrons. Right? That's an understanding in a wave picture. The other thing that was hypothesized was that if you came with a higher intensity, that would give faster electrons. Well, why did they think that? Well, if you're thinking of light as a wave, what does intensity mean? Well, that's taller peaks. All right, that's like bigger peaks. Well, if you're kind of thinking of as each peak slapping the surface, that's basically like harder slaps. Okay. Well, then they thought that each peak would come and slap the electron off, and then giving faster electrons. Right. So that was the hypothesis. That's what was expected under a wave picture of light. Well, we wouldn't be talking about this if it weren't a big surprise. When they did this, the results of the experiment were exactly the opposite. What they found was dead opposite. In fact, higher frequency. Instead of yielding more electrons, it actually yielded faster electrons. And turning up the intensity or the brightness gave more. Right? Well, what's happening here is instead of being in a wave picture of light, what this is necessitating a photon picture of light. Right? Or thinking of light as coming in bunches. Well, the easiest thing to wrap your head around with all this, I think, would be this idea that, okay, well, higher intensity yields more electrons. Well, so if you turn up the intensity or brighter light, so brighter light, the idea is to not think of that as taller wave peaks, but rather instead to think of that as more photons, more little chunks of light. Well, and then if each photon is responsible for knocking an electron off, well, then you get more electrons. Right? The tougher one to come up with was this one. And the idea here is that as you turn the frequency up, that each one of these photons, each photon actually has more energy. So that's basically like a harder slap to the surface. Okay, each photon coming down, it's a more vicious photon if it's a higher frequency photon. So that's kind of like harder slaps to the surface. All right, faster electrons. So this was really the tougher part to get. This was the big jump, is that not associating higher frequency just with something with wave peaks happening more often, but to completely shift the picture of light is that higher frequency light has each little packet, each little bit of light has more of a punch, right? And so what was developed from that, and the most important kind of relationship that comes from this, is the energy of a single photon, which is written like this. Use a little gamma usually to represent a photon. Energy of a single photon is proportional to the frequency. So this is a constant called Planck's constant. And then this is the frequency. Sometimes the chemists like to use different notations. Sometimes instead of calling this HF, they'll call it H nu. And that's partly because they like to reserve F for this quantity that's called fugacity that frankly don't use it, many people don't use that much. But in the physicists tend to write it like this, okay, HF. And so the idea with the photoelectric effect, again, is that if you go from a wave picture, the idea with making higher frequency light is that you have wave peaks that are coming more often. So you slap the surface more often, you get a whole bunch more electrons. That was the hypothesis. Higher intensity under a wave picture is bigger peaks. Each peak coming in, hitting the surface harder and making electrons come up faster. The reality is that it actually works more like this when you conduct the experiment. It seems that light's coming in these little bunches. If you make the light brighter or higher intensity, there's actually more bunches of light then. And then each little bit of light kicks off an electron, so you get more electrons. And then the real big leap was to say that higher frequency light, really what that means is that each little bit of light, each little bit has more energy. And so it's a more fierce photon coming down, and that gives more energy to the electron then when it comes off. So to quantitatively describe what's happening here, you can really use, come at it from an energy point of view. So the idea is, here's some energy that the light brings in, right? The electron comes off with some kinetic energy, right? Ke of the electron. The idea is that it takes a certain amount of energy just to get the electrons out of the metal. So we'll say it takes an amount of energy that we're going to call that amount of energy phi to get the electron out. And so what you can do is you can say, well, okay, I brought in this much, so here's the energy that I bring in, right? And then what happens is the electron that comes off has a certain amount of energy, and then this is plus whatever you lost on the way out, getting out of the metal, okay? So the energy that you brought in, right, that's the total number of joules you brought in. Some of that went into fishing this electron out, just to get it out. And then whatever is left over is this, okay? So this is basically what's brought in. This is used getting the electron out, and then this is left over. And so that's why sometimes you'll even see this thing written, instead of writing it in this order, saying, okay, this is all the energy that I had before, and this is basically accounting for it after. Sometimes you'll see it written slightly differently, or just thinking about it in like a little bit different logic, that the amount of energy the electrons have when they come off, it's equal to what you brought in minus what you lost. What you brought in minus what you lost. So the Ke of the electron is equal to the energy of the photon, HF, minus what you lost. So this relationship, or this cartoon, if you can kind of think of that when you're thinking of the photoelectric effect, you get pretty far with that. So if you're reading a little photoelectric effect problem, just kind of draw this little picture and just think about that. What the electron comes off with, it's what you brought in minus what you lost.